So this is our TS diagram. This is the saturation line for the R134A. So if we can have 100, this is 100 kPa, meaning that this temperature we are getting around minus 26 degrees C. So this is based on this table. Okay, so we are getting this value. All right. So if we can go lower than that, then we could get much lower temperature. So if we have a heat exchanger, let's say we have a heat exchanger. Well, let's say this is our heat exchanger, whereby this is the R134A coming into the heat exchanger. This is the outlet of the heat exchanger. Then let me correct the direction first. Let's say this is the way. Okay, because from here becoming this saturated liquid becoming saturated vapor. So if we could have this 100 kPa inside coming into the heat exchanger, and we have minus 26, meaning that if we have a chamber, okay, let's say we have a chamber right here, then if we put anything inside this chamber, let's say initially at room temperature at 27 degrees C, so we have right here the cooling of this saturated refrigerant at minus 26 degrees C, meaning that the heat from this substance or anything that we want to cool down will be transferred to the R134A. Okay, as though that this substance that we want to cool down is heating the R134A. Okay, this is what happened. Okay, this is what happened in our refrigerator. Okay, so this is our refrigerator in our house. Refrigerator in our house. So we open the door and then we put something inside the refrigerator. Then this heat exchanger or this flowing of R134A usually is located at the freezer compartment. Okay, this is usually located at the freezer compartment, whereby we usually make ice cubes or anything we want to freeze, we are going to put inside this evaporator side or the freezer side. Okay, whereas that the substance or any food or any material that we don't want to freeze it, then we put at the bottom part. Okay, so there is still cooling effect, but it's not as much what we put in the freezer part, because the freezer part is the coldest, right? The most minimum temperature that we could have. So what we can do right here is we want to create this environment. Let's say we want to create 100 degrees C minus 26. So we must create this environment of 100 kPa and this minus 26 degrees C, which have a control volume inside the freezer side. So what we can use right here is to get 100 kPa. So how we are going to get 100 kPa and having the cooling effect at 26 degrees C? So usually what we do is we must have a compressor right here because we want to bring down the pressure. Okay, we must bring down the pressure. So if we want to bring down the pressure, meaning that we must have one component or one flow device which can give us a low pressure. Usually for a compressor at the suction side will give us a low pressure. Okay, sorry, this is not the right way to sketch the compressor. Okay, let me correct it. So this is the compressor. So we want to create an environment having the pressure low the atmospheric pressure. So this is at atmospheric pressure. Maybe we want to go to 80 degrees C. So if you want to go to 80 degrees C, meaning that we have to create a vacuum in this line, okay, in the refrigeration line system, or in the refrigerant flow, we must create a vacuum kind of pressure, which is less than at the atmospheric pressure. So how to get it is to put a compressor right here, and at the suction side, we could have a pressure of less than 100 kPa. So this is a compressor. Then we compress the refrigerant up to what pressure? Up to the pressure whereby we are going to reject this heat. Okay, this heat absorbed. Let's say this is the heat, we heat the absorbed heat in the freezer. We want to throw it away, we want to reject it at the environment. So this is what we are going to reject at the environment. Okay? So this is what we have. So what is the temperature like in this part, in this device of this heat exchanger? Usually what we have right here is we have a fan. Okay, we have a fan. And the fan is run by a motor, electrical motor. If we want to look at our refrigerator, this usually is sited at the rear side of the refrigerator. So if the environment is at 30 degrees C, so how we want to transfer the heat from the refrigerant to the environment at 30 degrees C? So we must have temperature difference between the environment and also at this refrigerant at this side, at this heat exchanger where we want to reject the heat to the environment. Okay, let's say this one I change not to QE, but I put here as the Q naught. Okay, Q naught, which is rejected to the environment. Okay, so if we want to reject the heat at this device, which is called at the heat exchanger, then the refrigerant inside this device must be greater than 30 degrees C. So if greater than 30 degrees C, if we look at the property table, so how to get a more than 30 degrees C? So this is our 30 degrees C. It's 700. Okay? Let's say we want to have a 10 degrees C difference. If you want to have a 10 degrees C difference, then we need to get around this figure. Okay, at 90, or maybe we put at 1000. Okay, 1000. 1000 is about 10 bar. Okay, 1000, is it 10 bar? Divided by 100. Yeah, it's 10 bar. Okay, so now what we could create is to have the refrigerant to be compressed up to 1000 kPa. And if this 1000 kPa, then we are going to have this T set at 39.37. It's about 40. Okay, it's about 40. So now we have the refrigerant flowing right here is at 40 degrees C. So we have a temperature difference of 10. Then we could reject the heat absorbed right here. Okay, the heat absorbed right here to be rejected to the environment, where the environment is 30 degrees C. Now we have this 40 degrees C. Okay, we are going to compress to 1000 kPa. Then after that, we are going to get the 100 kPa again. Okay, we have to get the 100 kPa again. So meaning that from 1000 kPa, we are going to expand. Okay, we are going to release the pressure to 100 kPa again, so that we could get minus 26 degrees C. Because we want to create this environment of cold space in order to cool anything inside the freezer or inside the refrigerator. So if we want to bring down pressure, then what we do, we have expansion device. Or maybe we can use right here the expansion engine. Okay, expansion engine. So what we must have right here is the expansion process. How do I sketch the expansion process? Okay, this is the device for expansion. It can be used as a turbine. turbine is one of the expansion device. So we flow in and the flow out is getting 100 kPa again. So this is the what we call as the refrigeration cycle. Okay, whereby we have compressor. Of course, the compressor we are going to put in work. And for a turbine, of course, we are going to have work out. And this Q inside here, this is the Q where we absorb at the cold space. So this is what we call as the refrigeration system. And these are all the devices that we could have in our system. So the first device is the place whereby we have the cooling effect. And then we have the compressor. Why we need the compressor? We need the compressor for creating the pressure of 100 kPa in order to get minus 26, the cooling effect, low temperature. And how much pressure that we have to compress? We have to compress to 1000 kPa. Why to 1000 kPa? Because we want to have the difference temperature between the refrigerant and the environment, where the environment is the place whereby we reject the Q from this Q absorb. Okay, we are going to reject this Q absorb at this device, which is called as the heat exchanger. And then after that, we are going to expand it at the turbine. Why we want to expand it? Because we want to create the 100 kPa again. You see here, we have compressed at 1000. Now we want to get again 100 kPa. So we use an expansion device. In this case, the expansion device we use is the turbine. Or maybe we can use the expansion or the expander from pistons in the device. It doesn't matter as long we use the expansion device. Okay, so if we could sketch the diagram in this case, so this is the pressure of 1000, and then we have again another pressure of the 1000 kPa, which give us the pressure right here about 40 degrees C, right? Then if we look at the temperature of the things that we want to cool down is QA. So this is the part whereby we have the actual temperature that we want to transfer. Okay, this is the food compartment temperature. I put right here is about 27 degrees C. And right here, we have the temperature of the environment. And this is at, the environment is at, let's say, 30 degrees C. And right here, we are going to have the T set at this part, which is about 40 degrees C. So we have a heat transfer right here, whereby we have the heat transfer from the material that we want to cool down, which in this case, I give the name as QA. And then we have the rejection of heat from this, right? From this pressure of 1000, which gives us the T set of 40. Then right here, we have another heat transfer, is Q. Okay, this is the Q for Q naught. So this is, if we look at the pressure, why we use 100 kPa, why we choose 1000 kPa, and we look at what device that we are going to use in this case. Right. Now, what we are going to look at the first cycle of this refrigeration system, where it uses these four main components. Okay. So the main component right here, this is the heat exchanger, this is the heat exchanger. Now we are going to give a special name for those heat exchanger, where this type of heat exchanger, we are going to call it as evaporator. Okay, this is compressor, of course. And this device, the heat exchanger at this side, which we reject the heat to the environment. This we call as the condenser. Okay, this is evaporator. What is meaning of evaporator? From liquid, we change the phase of the R134A from liquid to vapor. So it called as the evaporator. And then right here, we cool down the refrigerant. Therefore, from superheated vapor or maybe vapor, we are going to condense it. So how to condense it? We condense it by rejecting the energy inside the refrigerant. So it will become vapor, becoming as the liquid state. So it's called as condenser. We are going to change the phase from vapor to liquid. Okay, and this is called as the turbine, as the expansion device or the expander. So this type of device, right, if we have this evaporator, compressor, condenser, we have the expansion device or the expansion engine, and if we assume that everything is reversible, all processes are reversible. At condenser, we assume as reversible and isothermal. This is reversible and isothermal. The compressor as reversible and adiabatic. The turbine as reversible and adiabatic. Then this cycle is called as the reverse Carnot cycle. So this type of component having all the processes that I mentioned just now. So this is called as the reverse Carnot cycle. Okay, reverse Carnot cycle. Again, in this part, we are going to have the process of heat absorption, reversible and isothermal heat absorption. Here we have reversible adiabatic compression. Here we have the isothermal, reversible isothermal heat rejection. This is, we are having the reversible adiabatic expansion. In other words, we could sketch the refrigerant cycle on the TS diagram. So let us get the cycle on TS. Okay. So this is our rejection. This is our compression. This is our expansion. This is our heat absorb. So let's say this is 0.1, this is 0.2, this is 0.3, this is 0.4. Right? So right here, we are going to have the heat absorb Q41. This we are going to have the Q reject, which is Q23. Here we are going to put in work W12. Here we are going to reproduce some work, which is called as the W34. So this is the cycle sketch on the TS diagram, which is called as the reverse Carnot cycle. Okay, so from the flow or the SFEE, steady flow energy equation, so we could write the work and heat for every processes. So as usual, the W12 is equal to H2 minus H1, and then the W34 is equal to H3 minus H4. The Q41 is equal to H1 minus H4, and for the Q23 is equal to H2 minus H3. So this is all the enthalpy change in order to get the work and the heat. Okay, the work and heat transfer, the work transfer and the heat transfer. So this is how we sketch the reverse Carnot cycle on TS diagram for R134A. And remember, I mentioned just now, 1, 2 is the reversible adiabatic compression, which is also known as the isentropic compression, where the S is constant. 2 to 3 is the reversible isothermal heat rejection. 2 to 3, P constant and T constant. Okay, P constant and T constant. And then 3 to 4 is the reversible adiabatic expansion, whereby this is also known as the isentropic expansion. The S3 is equal to S4. And then lastly is a 4 to 1 is the reversible isothermal heat absorption. Okay, so the cooling effect that we have is 4 to 1. So if you want to have cold space, then we need to put at the process of 4 to 1. So if we write the state at this cycle, this schematic diagram, then this should be at state 1, this is state 2, this is state 3, and this is state 4. Okay, this is state 4. So this is 1, 2, 3, and 4. So this is what we have and call as the reverse Carnot cycle. Then we are going to use this to have the cooling effect. So the cooling effect is at 4 to 1. If you could remember that when we learn in thermodynamics, we have this type of schematic diagram as far as the second law is concerned. So this is our refrigerator, this is our QH, this is our QL, this is our TL, and this is our TH, and we has the W net in. Okay? If I could relate this, what we have learned in the second law of thermodynamics with all the reverse Carnot cycle terminologies, then this QH is equivalent to the Q23. This QL is equivalent to Q41. And this W net in is equivalent to the W34 minus W12. Or if you want to have a positive sign of this W net in, then we could write here as the W12 minus W34. This is the amount, the magnitude of W that we are going to put in this refrigerator. So if this refrigerator consists of the 4 components that I mentioned just now, and the processes fulfill with what I have mentioned, describe the process of 1, 2, 2, 3, 3, 4, and 4, 1. So this refrigerator is a reversible refrigerator. Okay, the reversible refrigerator always work, or the principle of this working, the principle of this reversible refrigerator always follow the reverse Carnot cycle of refrigerator. Okay, so for a refrigerator, then we want to have Q41. So if the Q41 is the main concern, which is our interest. So to see the performance or the quality of this refrigerator, then we are going to have one parameter that we have learned called as the COP refrigerator, which is equal to the desired output, which is our Q41, divided by our required input, which is W12, okay, or the W net in this case. And for a cycle, this could be written as Q41 divided by W net in. The W net in for a cycle is equal to the summation of Q. Okay, the summation of Q. And in this case, the summation of Q is the Q rejected, Q23 minus Q41. Okay, Q23 minus Q41. And apart from the Q41 could be obtained from the difference in enthalpy, because this is the isothermal heat absorption and this is the isothermal heat rejection. So we could also could write also the Q41 as equal to constant temperature. This is T1 S1 minus S4. This is from the definition of entropy change. And also the Q23 could be written as the T2 S2 minus S3. And we know that in this case, the S2 equal to S1 and also the S3 is equal to S4. Okay, and this COPR for a reversible Carnot cycle, we could write as the COPR for reversible Carnot cycle is equal to T1 S1 minus S4 divided by Q23 is a T2, okay, T2 S1 minus S4, sorry, S1 minus S4, and Q41 is T1 S1 minus S4. Then this delta S could be cancelled off. What left is T1 over T2 minus T1. Okay, so for a reversible Carnot cycle or the COP for reversible, it could be write as T1 divided by T2 minus T1. It's a function of the temperature of T1 and T2. What is T1? T1 is the T set at the evaporator. And what is T2? T2 is the T set at this pressure. Okay, T set at the condenser pressure. Just now, we have this temperature of 26, minus 26, and also 40. So if this the temperature involved, so what we could have right here, this is equal to T1 is minus 26 plus 273 divided by the T2 is at 40 minus 20, sorry. Okay, this is T2 is 40 minus 26. So can you calculate how much that we are going to expect the COP? Can you calculate for me that value? What do we have? You guys?
3.74.
3.74. Okay, so we are going to have, if you look at the equation of this, okay, the equation of this, then we are going to have 3.47. So what is the meaning of that? If we put in one work, we are going to absorb 3.47 heat of this amount. Okay, we are going to have the heat is 3.47 times more compared to the input of the work. Okay, so this is if we want to have, okay, if we want to have the cycle as a refrigerator. The same cycle also can be used as the heat pump, right? Heat pump. If you want to use the same cycle as the heat pump, then our interest is at this side, the Q23. What is the heating effect of this refrigerator? Okay, so if this refrigerator is working as a heat pump, for heat pump, which give us the heating effect, then we have another coefficient of performance which is called as the COP heat pump. Okay, COP heat pump. This is COP heat pump, and the definition is the amount of heat rejected divided by the W net in. And for a COP heat pump, for a reversible, this is equal to the T2 divided by T2 minus T1. This can be proved. What we have done for the COP refrigerator, the COP refrigerator, in this case, is a Q for 1. But in this case, for heat pump, is Q23. Then we are going to have T2 divided by T2 minus T1. Okay, guys? So that is the analysis for a reversible Carnot cycle or reversible refrigerator, which is called also as the reverse Carnot cycle. Right. But as we know, the reverse Carnot cycle, everything that is based on Carnot cycle is usually a theoretical cycle, which is the theoretical limit that we could have and can be used as the guide to design the actual system, which in this case, we are talking about refrigerator and heat pump. Okay, refrigerator and heat pump. So in Malaysia, usually we are going to have the refrigerating effect, whereby we are going to use the refrigerator in order to cool down, because we are a tropical country, so we want to have a space that is being cooled or aircon. Then we use this refrigerator. In Malaysia, we seldom use the heat pump. But in temperate country in Europe, usually they are using heat pump in order to warm space, usually in confined space, right? In the house, in the room, and etc. Okay, guys? So this is analysis based on the reverse Carnot cycle. And we know that a reverse Carnot cycle is not a practical cycle because it consists of reversible processes. You see, from 1 to 2, 2 to 3, 3 to 4, 4 to 1, all the processes begin with the words of reversible. We have reversible adiabatic at compressor and at the turbine. We have reversible isothermal at the condenser and also at the evaporator. So it's not a practical cycle. So now we are going to look at more towards the practical cycle, whereby if we look at Carnot cycle, we have a turbine. Okay, we have a turbine for getting a low temperature or low pressure in order to get low temperature. So we are going to use turbine right here. But as we know, you see, this state of 3 is already saturated liquid. Okay, saturated liquid. And state 4 is mixture. So the amount of work we are going to have from W34 is very small. Okay, it's very small. Maybe the turbine itself won't rotate because of the small energy content of 3. Usually, if you want to have a very high work, then we need to put the state of the substance or the working fluid. Usually, we put at the superheated vapor phase, as what we did for the steam power plant. Always at the superheated. Then we have a lot of energy. Then we could have a lot of work output. But in this case, the using of the expansion engine for 3-4 is the main purpose is to get a low pressure. Okay, from 1000 to 100, that is the main purpose. But for having a device such as a turbine, which is costly, and the amount of work that we are going to have very small because the state 3 is saturated liquid, the source of energy is very small, then we are going to have W34 is very small. So compare with the device that we have to put as a turbine, which is costly, then what we need is just a device which can have the expansion effect so that we could have high pressure to low pressure. So if we remember what we have learned in flow devices in steady flow energy equation from first law of thermodynamics, the device which can give us a low pressure is the expansion device or the throttle valve. Okay, a throttle valve. So we try to put this reverse Carnot cycle towards a more practical type of cycle. Then the schematic of that cycle will become as this. Of course, we have our turbine, the compressor right here, and then we have our evaporator. Then the expansion engine or the expander right here, we are going to use the device called what I mentioned just now as the throttle valve. So now we have a new device. Okay, or sometimes called as the expansion valve. Okay, we can call it as expansion valve, we can call it as the throttle valve, all the same meaning, or throttle valve. Right? Sometimes I call it as expansion, a thermal expansion valve. So this is our cooling effect having right here. This is our evaporator. This is work input, our turbine. This is our heat rejection at the condenser side. At this expansion valve, we don't have any work input or any work output. What we have is just the drop in pressure. And if we know, if we could remember that the flow device, for a flow device, the time of process that we could have is what being called as the isentropic process, whereby the enthalpy does not change. Okay, so if I put right here, this is state 1, state 2, state 3, and this is state 4, meaning that for expansion valve, we are going to have H3 is equal to H4. Okay, so when we change the expansion engine as a throttle valve, so the whole thing of this cycle is no more a reverse Carnot cycle, but it is called as the vapor compression refrigeration cycle. Okay, vapor compression refrigeration cycle, which I usually refer as VCRC. So this is a vapor compression, refrigeration cycle. This is the type of system which is normally used right now. Nowadays, if we look at our refrigerator in our house, the domestic type of refrigerator, is all based on this vapor compression refrigeration cycle. So, if we sketch this cycle on the TS diagram, so of course, heat rejection, same profile, and then we have compression process, same profile. Okay, this is our pressure of evaporator side. This is pressure. If this is 1, 2, and 3. Now, for isentropic process, we are going to sketch the process 3 to 4 as this, which is highly irreversible process. And we actually don't know what is the actual enthalpy line in the TS diagram. So what we could sketch here is not a continuous line, but is a dotted line. Okay, so this represents the process of throttling from 3 to 4. Okay, from 3 to 4. So now again, of course, the W in right here is 1, 2. Same formula, H2 minus H1. And then the heat rejection right here is W3, 2, 3, H2 minus H3. And then the Q absorbed in the evaporator, 4, 1. So, if we look at the formula of COP for this refrigerator, so we cannot put reversible. This is not a reversible type of cycle because the 3 to 4 we assume as highly irreversible process. That's why we have H3 minus H4. Then this should be defined and obtained through the definition of the COPR, which is equal to Q41 divided by W net in. In this case, the W net in is only 1, which represent as the work input to the turbine. Okay, the work input to the turbine. There's no work 3, 4. So here we could write as W12. And to get the Q41, W12, we cannot use the change of T time change of entropy. We need to get everything in terms of enthalpy. Okay, Q41, H1 minus H4, W12, H2 minus H1. So this is for the coefficient of performance, the quality, the efficiency of our cycle. If we run this cycle as a refrigerator, so we call it as COPR. If the same cycle running as heat pump, so we could define right here, this is Q23 divided by W12. So this is the performance, the quality, the efficiency of our VCRC. Remember, this is called as the VCRC, Vapor Compression Refrigeration Cycle. The drawback of this type of cycle, you see, the Q41. Let us analyze the Q41. Previously, from the reverse Carnot cycle, the Q41 begin at this point. Okay, this is for a Carnot cycle, reverse Carnot cycle. initially, this is our point of 4. So for a reverse Carnot cycle, the heat effect or the cooling effect is from this 4 to 1. So if we look at this change of enthalpy, the H1 minus H4 for reverse Carnot cycle is greater compared to this VCRC. The VCRC, we only obtain H1 minus H4, where the H4 is higher than the H4 for a reverse Carnot cycle. So in this case, we are going to have the drop in Q41. The drop of Q41. Our interest, if you want to have this cycle as for refrigerator cycle, then we need to increase the Q41. That is our interest. That is our main purpose to work as VCRC, because it's called as the refrigeration cycle. So of course, for a refrigeration cycle, we want the cooling effect. The cooling effect is always at 4.1 at the evaporator side. So then we need to get more 4.1. We need to get more Q41. We need to expand or to make the difference in enthalpy H1 minus H4 as bigger as possible. So now what we are going to do next is to move the point 1. Okay? We are going to move the point 1 to the right so that what we could have more enthalpy change 4 to 1. Okay? So next modification or the next method how to increase the Q41. So now the method or the main purpose is to increase Q41. We are going to use the same component. The same component, we have the turbine, we have the condenser, we have the expansion valve, we have the evaporator, but we are going to change the process at the evaporator side. So what we are going to do, we are going to move point 1 to the saturated vapor. Okay, we are going to move the point 1 at the saturated vapor. So if we move the point 1 as the saturated vapor, so at the end of the compression process, we are going to have state of superheated. Okay, this is 1, this is 2. So this is superheated. And then we continue the condensation process at the condenser side. 3 to 3, 2 to 3. We assume 3 still is the saturated liquid. Then we have the expansion process, whereby the same as the previous process. So this is 3 to 4. You see now we have make the increment of delta H. The formula is still the same, but our 4 to 1 now is greater compared to the previous cycle, whereby we have the end of the compression process is at the saturated vapor. Okay, guys. So now this is the first modification we are going to do. So we are going to increase the Q for 1. Okay. So remember, the first cycle is the end of the compression process 2 is at saturated vapor. Now the second, to increase the Q for 1, we are going to project point 1 or the end of the evaporation process is at the state of saturated vapor. Then the state 2 will become as the superheated vapor. Again, we want to further increase the Q for 1. Then what we do, we are going to introduce the compression process, the beginning as compression process at the superheated vapor side. Okay, so let us look at this modification. As far as the component is concerned, the same component will be used. The four main components, which is the turbine, the condenser, the expansion valve, and the evaporator. But the state is different. We are going to change the state 1. Now we are touching on the state 1 to increase the Q for 1. Okay, so this is the first method used in order to increase the Q for 1. Now we are going to the second method, how we can increase the Q for 1 by moving the point 1 or the state 1 to the right. So we have moved the first one, we have moved to the saturated vapor. Now we are going to move it to the superheated vapor. This is our pressure of our evaporator. This is our pressure of our condenser. Now we are going to move our point 1 up to here, whereby we have the beginning of the compression process as the superheated vapor. So right now, this is our compression process. 1, 2, and then 2 to 3, the condensation process. And again, 3 to 4, 4 to 1. As far as the formula is concerned, the steady flow energy equation, the energy balance is concerned, is the same. W turbine, H2 minus H1, Q condenser, H2 minus H3, H3 equal to H4, and then for the Q absorb, or the also known as the cooling effect or the refrigeration effect, H1 minus H4. So now we can see that from 4 to 1 saturated vapor, by increasing as superheated vapor, we are going to have more Q for 1. But we are going to reject more heat. We are going to input more work. So more work in, we are going to have more Q absorb. Okay? So this is the maximum side or the second method whereby we are going to increase the cooling effect, which is increase the change in enthalpy at the evaporator side. Okay? Next, what we are going to move the point 3. Okay, before that, I'm going to define, usually sometime this delta T, okay, this is delta T, which is the T1 minus T set. Okay, this delta T is defined as the T1 minus T set. Where is the T set? The T set at the pressure of evaporator. Okay, So we can define this as delta T. And this delta T is also known as the degree of superheat. Okay, degree of superheat. So when we have a parameter named as degree of superheat, meaning that the degree of superheat is the temperature of T1 minus the T set. T set at the pressure of evaporator. So that is called as degree of superheat. Okay. And then after that, we could get more Q for 1 by modifying the state of 3. So next, what we are going to do, we still have the discussion of increasing the Q for 1. But now we are going to move the state of 3. Again, I'm going to repeat, this, as far as the schematic diagram is concerned, we still have the four main components. There is a turbine, the condenser, the throttle valve or expansion valve, and the evaporator. What we are going to use, we are going to do is just to move the states. So now we are going to look how the third method we are going to increase the Q for 1. This is our pressure of evaporator. This is our pressure of condenser, right? And then assuming that we have a superheated vapor going into the compressor, 1, 2, then we are going to move the point 3 towards the compressed liquid region. So let's say this is our point 3 at the compressed liquid region. And now this is our process 2 to 3 at the condenser side, which is the rejected heat. Then now we have the process of throttling at the expansion valve 3 to 4. Then we have the evaporation process, which are going to give our cooling effect. You see now we have increased furthermore the Q for 1, you see, by moving the state of 3 towards the compressed liquid region. As far as the equation, energy balance, the steady flow energy equation is concerned, they are still the same. W12 H2 minus H1, Q23 H2 minus H3, H3 equal to H4, and then the Q for 1 is equal to H1 minus H4. Okay? So this is all the purpose to increase the Q for 1. And then again, there's one more term that we are going to be introduced. This state 3, okay, this state 3 is also known as the state of subcool. Okay? State 3 is also known as the subcool condition, which is the temperature of T3 is lower than the T set at the evaporators, at the condenser side. Okay, if this is our T set, at the condenser, then if we have a subcool type of condition at point 3, state 3, then we can write here the T3 is less than the T set at the P for the condenser. Then we are going to have, as what we have learned previously in thermodynamic in pure substance, this is called as compressed liquid. And right now, we can also write this or subcool region. And if we can write the delta T right here, which is equal to the T set minus T3, this is also known as the degree of subcool. Okay, degree of subcool. And we can write this delta T, we can sketch the delta T in our TS diagram. So this is what is called as the delta T, degree of subcool. And the delta T is defined as the T set minus T3. So now we have two terms. One is the degree of superheat, and another term called as the degree of subcool. Okay? And this for the ideal cases. All this modification is done on the VCRC, Vapor Compression Refrigeration Cycle. And if we look at the compressor side, sometimes we have what is called as the isentropic efficiency, which is not an ideal compression process in our compressor. We have losses or we have irreversibilities. So in this compressor side, sometimes we could have the isentropic efficiency. So if we have the isentropic efficiency, then our beginning of condensation process will begin at 2 at this point. So this is our 2 from this point, and this is our 2s. Cos, what is the definition of the isentropic for the compressor? So this is as the isentropic work W1 2S divided by W actual work 1 2. This is equal to H2S minus H1 divided by H2 minus H1. So this is not an ideal case. Okay, not an ideal case whereby we have losses or we have irreversibilities at the compressor side. Okay, so this is the analysis from reverse Carnot cycle. We go for the VCRC, and then after that we look at the VCRC. Why? How do we increase the cooling effect? By putting 0.1 as superheated vapor, or putting the 0.1, firstly putting the 0.1 at saturated vapor, secondly putting the 0.1 at superheated vapor. After that, we change the state of 3 from saturated liquid to subcooled region. So this method, everything is in order to increase the Q41. Okay? Any question, guys? Any question? No question. Okay. If no question right now, we try to look at one example. Tutorial refrigeration. Tutorial refrigeration. This one. Okay. So let us look at the first example, level 1. So let me copy that for you all. We try to solve the 11.1, 11.2, sorry. 11.2. Copy. Let's start at the fresh canvas. Paste. Okay. A steady flow Carnot refrigerant cycle uses R134A as the working fluid. The refrigerant changes from saturated vapor to saturated liquid at 30 degrees C in the condenser. It rejects heat. The evaporator pressure is 160 kPa. Show the cycle on the TS diagram relative to saturation line and determine. Okay, so as we know that a Carnot cycle consists of 4 main components. One is the compressor, then we go for the condenser. The third one is we go for the expansion machine or expander or the turbine. And then after that, we go for the evaporator. And if we sketch the TS diagram for a reverse Carnot cycle, or in this case called also known as the Carnot refrigeration cycle, then the whole cycle, we know that we must sketch it in the saturation line region. Okay, so this is our pressure of evaporator, pressure of condenser. This is our state 1 isentropic compression, 2 to 3 reversible isothermal heat rejection, 3 to 4 reversible adiabatic expansion, and 4 to 1 is a reversible isothermal heat absorption. Okay, and given here, the refrigerant changes from saturated vapor to saturated liquid at 30 degrees C in the condenser. So now at the condenser side, we are having right here, the temperature is a 30 degrees C. Okay, whereby we reject the heat from the condenser. The evaporator pressure is 160 kPa. So in this case, this pressure is 160 kPa. Okay, whereby we have the P1 is equal to the P4, which is equal to the 160 kPa. And if we look at our table, at 160 kPa, the T set is 160 kPa, the T set is 1560 minus 15.60 degree C. Okay, so that is the temperature involved. As far as the reverse Carnot is concerned, we need to get the temperature. So in part A, we don't need to prove what is the state 1, 2, 3, 4. Because for a reverse Carnot cycle, what we have learned, it must be a rectangle type of cycle, and those points or states must be in the saturation line. This is what we have sketched, as what we have sketched right now. So in this case, to solve for the part A, what is part A? The COPR for reverse Carnot cycle. So this is a reversible cycle. This is equal to the T1 divided by T2 minus T1. What is T1? T1 is minus 15.60 plus 273 divided by T2 is 30. This is 30 minus 15.60. So can someone calculate? How much is that COP? You guys, you must have the COP around 6, 8, 7, and etc. If you get a very awkward number, hundreds, or maybe you can get 20 something or 40 something, that is not right. Okay, and then make sure that everything is in Kelvin. Okay, so this I have converted to Kelvin. And this 30 minus 15.6, this is already in delta T Kelvin. Because we know that the delta T in Celsius is equal to the delta T in Kelvin. Okay? That's why right here I don't need to plus 30 plus 273 and also I don't need to put minus 15.60 plus 273 because the positive 273 and the negative 273 will be cancelled off. So I just put right here the delta. But in this T1 at the top, you need to get in Kelvin, then you need to plus 273. So can someone give me what is the COPR in this case?
5.64.
5.64. Okay. So that is part A. And then for part B, we are going to get the amount of heat absorbed from the refrigerated space, okay, which is Q for 1. Right? And this Q for 1, we could get it from the H1 minus H4. If we use this formula, then we need to get the H1 is equal to HF1 plus X1 HFG1. Then we need to get the X. The X1 we could get from the S1 equal to S2. Okay, we could obtain the Sx1 is equal to S1 minus S2. Same goes for the H4. We could get the H4 equal to HF4 plus X4 HFG4. And in this case, our X4 we could get from the S3 is equal to S4. Okay? We also can get from COP. COPR for reverse Carnot cycle, which is equal to the Q for 1 divided by the Q, Q for 1 divided by W1, 2. Okay, and this is equal to Q for 1 divided by Q23 minus Q for 1. And this is equal to, can we write, can we reduce that? No. Okay. So we have the COP. We want to get the Q for 1. Right? Then in this case, if you want to know what is Q for 1, we need to get the Q23. So what is Q23? Because the Q23 is based on the isothermal heat rejection, then we could write here this is as T2 S3 minus S2, where the S3, where is S3? The S3 is SF and the S2 is SG. This is equal to T2 SFG2, whereby the SFG2 is at 30 degree C. Okay? So when we solve the Q23, then we could solve the Q41. Let's try to get the Q23. Q23 is equal to, what is our T2? T2 is 30 plus 273 multiplied by the SFG at 30 degrees C. SFG at 30 degrees C, let us look. What is the SFG at 30 degrees C? So this is our 30 degrees C. And where is our SFG? This is our SFG. This is 0.57091. Okay, so please, can someone calculate for me? What is the Q23? This
172.
172.
0.98.
This is a kilojoule over kilogram. The S3 is equal to SF, S2 is equal to SG. Sorry. Terbalik guys, this one. I should put right here, this is not the right sequence. Okay, let me write that again. This is S3 minus S2. So this is our SG. Salah lagi. This is S2 minus S3. So the S2 is Sg, the S3 is Sf. That's right. That's why we have SFG. Okay, so please calculate what is the Q for one. Okay, once you have solved your Q23, we got our COP as a 6 something just now. Then get the Q41. 5.64. This is for the COP. Six one is equal to Q1 divided by 172.98 minus Q41. Okay, anyone? Yes, anyone? Q41?
One four six point nine three.
146.93. Sorry. 146.93. Okay, can someone verify? Please?
Correct, sir.
Okay, thank you very much. So this is Q41. Then next we are going to get the work net input. So the work net input, again, we are going to use the COP. COP R ref is equal to Q41 divided by the W net in. In this case, our W net in, take note, in this case, the W net in for this reverse Carnot cycle is equal to the W12 minus W34. But if we want to get from the W, it's quite tedious because we need to get all the X value of 3 and also of 4 and also as for 1. Okay, so it's quite tedious and quite lengthy. So what we use, we just use this formula. Because we know that we have solved for this value, we have solved for this value, then we are going to get the W net in. So from here, the W net, okay, in this case, the W net in is equal to Q41 divided by the COP ref R, COP R ref, COP R ref. Okay, Q41 146.93 divided by 5.61.
26.2.
26.2, eh? To what? To one more. Be consistent with your decimal point.
19. Just now 19.
19, eh? Okay. 19 kilojoule over kilogram. And then the last part is for D. This is the coefficient of performance in the system act as a heat pump. So this is part C. Part D. If the system act as a heat pump. So for a heat pump, COP heat pump. Sorry. Heat pump reversible. This is equal to T2 divided by T2 minus T1. What is T2? T2 just now is 30 plus 273 divided by 30 minus how much is now? The T set is 1560 minus 1560. Much? 6.61. Good. Can someone calculate? Verify? Is it 6.61?
6.64.
Lebih kurang, eh? So can you see this? As though that be plus 1. Okay? Or we, oh sorry. We can also use the value of COP, HP, ref is equal to Q23 divided by dW net in. Okay, so maybe you can use this formula to get the COPH pump. 172.98, Q23 is 172.98. Alamak, lupa dah. I just mentioned just now. Q23 is 172.98. 172.98. 172.98 divided by the W in, just now we get 26.19. 26.19. Okay, do we get same value? 6.6 something. Okay, berapa? 6.6? 4.
6.604.
604. This one, just now? Okay lah, yeah. We got about the same, eh? 6.6, 6.6. Okay? So we can use two methods. How to get? Okay. Any question, guys? So this is a reverse Carnot cycle. Okay, reverse Carnot cycle. Any question?
No, doctor.
All right. Next one, we are going to go for the VCRC. So let us look at the question of VCRC. Okay, 11. A commercial refrigerator. So as I mentioned just now, a commercial type of refrigerator usually consists of this VCRC. Okay, VCRC. Let us analyze first the question given. We don't look at the question asked, but we look at the description of the cycle first. Oh, this same as now. Salah. This is not the question. The question is, oh, 11. Okay. A commercial refrigerator with R134A as the working fluid is used to keep the refrigerated space at minus 30 degrees C by rejecting its waste heat to cooling water that enters the condenser at 18 degrees C at rate of 0.25 kg per second and leave at 26 degrees C. The refrigerant enters the condenser at 1.2 megapascal and 65 degrees C and leave at 42 degrees C. The inlet state of the compressor is 60 kPa and minus 34 degrees C, and the compressor is estimated to gain a net heat of 450 from the surrounding. Okay. So let us sketch the schematic diagram first. So what we have, a commercial refrigerator. We have our condenser. We have our refrigerated space. Usually we have the evaporator. Then we have a compressor. And the compressor is gaining heat from the surrounding at 450 watt. So let us sketch the schematic diagram. The first thing is our condenser. Then we have our compressor. Then after this, we have our expansion valve. Then we have our evaporator. Okay. Cause is state 1, state 2, state 3, and state 4. Condenser, evaporator, compressor, expansion valve. Okay, our expansion valve. Okay, using R134A, now we have the refrigerated space as minus 30 degrees C. So we need to maintain right here as minus 30 degrees C. By rejecting a waste heat to cooling water at the condenser side. So at the condenser side, we have cooling water. So we have cooling water flowing into the condenser. And it's mentioned that rejecting waste heat to cooling water that enters the condenser at 80 degrees C. So this is our T water in at 18 degrees C. And we have the M dot for cooling water as 0.25 kilogram per second and live at 26 degrees C. The TW naught out is at 26 degrees C. The refrigerant enters the condenser at 1.2 megapascal. Here is one, sorry, different color. This is enters the condenser at 1.2 MPa and the temperature is at 65 degrees C. So that is state 2, enters the condenser, which is equivalent to the outlet of the compressor. And leave at 42 degrees C. So this is leaving the condenser, the refrigerant leaving the condenser at 42 degrees C. The inlet state of the compressor is 60 minus 34. So the inlet of this compressor is at 60 kPa, which is vacuum. Okay, vacuum. And the pressure. The temperature is minus 34 degrees C. And then it's been said that the compressor is gaining heat. So this compressor is gaining heat. Q dot G by the compressor is equal to 450 watt. Okay, remember the 60 kPa is for the pressure of the evaporator. The minus 30 is the refrigerated space. Okay. So this is what we have. Right? So now what we do, we try to sketch. But before we sketch, we need to know what is the state of each point 1, 2, 3, and 4. We know that for this case, the H3 is equal to H4 at the expansion valve. Right? So what is the first question? Let us look first. What is the first question? The first question is to get the quality of the refrigerant at the evaporator inlet. Okay, the quality print screen paste. Let us take the first three questions. So copy. Okay, the quality of refrigerant at the evaporator inlet. Where is our evaporator inlet? The evaporator inlet is state 4. Okay, state 4. Right. So we still need to get part A. What is X? What is X3? X3 is equal to H3 minus HF3 divided by HFG3. And H3 is equal to, sorry, evaporator inlet is not 3, it's 4. This is 4, 4, 4, and 4. And H3 is equal to H4. Okay. And what is H4? H3 is based on what? The pressure of 1.2 megapascal and the temperature is 42 degree C. Okay, now we need to get the state of 3 in order to get the H3. So in order to get what is the state of 3, we need to get what is the T set right here at 1.2. Okay, so 1.2 megapascal, the T set 1.2 megapascal. 1.2 megapascal is 1,200. 1,200 is 46.29. 46.29. 46.29 degree C. Okay. And we compare the T set and also the T3, we can find that the T3 is less than the T set. Therefore, compressed liquid or subcool. Okay, you see, this is what we have learned just now. The T3 is less than the T set. The T set is 46 at 1.2. So the whole thing here for the condenser is working at 1.2 megapascal inlet and outlet, assuming there's no pressure drop. Okay, usually in our heat exchanger, we learn that the inlet and outlet for each flow, there's no pressure drop. The pressure is same. So we get this T3 is less than the T set at 1.2 megapascal, then it's subcooled. So when we find it's subcooled, then we know that the H3 is equal to the HF at given temperature 42 degrees C. So 42 degrees C will give us the enthalpy of 42 degrees C, the enthalpy, this is our enthalpy, HF, 111.26, 111.26, 111.26 kilojoule over kilogram. And once we have the H3, which is equal to H4, then we could get the X4, which is equal to H4, 111.26 minus HF4. 4 is at 60 kPa. At 60 kPa, this is 60 kPa, and the value of H, these are the value of H, is, so this is what What did I copy right here? Yeah, the value of HF, the first one HF. So this is 3.841 divided by the HFG is 223.95. Okay guys, can you get what is the value of X for? The quality?
0.447.
Okay, give me, if for X value, give me 4 decimal point.
0.4797.
97. Okay, thank you. So that is the quality for the part A. Right? So I think I will stop right here and we continue tomorrow, inshallah. So let me take your attendance first. Attendance 30 May 2423, send and copy. So please check your chat box. Control V, so that is your attendance, guys. Please sign in. Do you have any question, guys?
No, Doctor.
Tak ada, So if no question, then that is for today. So see you guys tomorrow, inshallah. Okay, Assalamualaikum.
Salam. Thank you, Doctor.
Salam. Thank you,
Bye
sir.
bye, guys. Welcome.
Thank you,
Bye bye,
Doctor.
guys. Bye bye, guys.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Welcome. Welcome.